Hey everyone. Welcome back to the channel. Today we're gonna talk about a topic that's essential for anyone working with power systems. Transformer connections. You've seen transformers everywhere. On utility poles. In substations. Inside industrial plants. But did you know that how you connect the windings matters just as much as the transformer itself? It really does. The connection type determines voltage ratios, current relationships, harmonic behavior, and even how transformers can be paralleled. By the end of this short lesson, you'll understand all four main connection types. Delta-delta, star-star, delta-star, star-delta. And you'll also understand vector groups. Let's get into it. Let's start with the first one. Delta-delta. Shown with this triangle symbol. In this connection, both the primary and secondary windings are connected in delta. Like a closed triangle. Each phase winding is connected between two lines. Now here's the important part. In a delta connection, the line voltage equals the phase voltage. So if you have 480 volts line to line, each phase winding also sees 480 volts. But the line current is square root of 3 times the phase current. So if each phase carries 100 amps, the line current is about 173 amps. One of the biggest advantages of delta-delta is that it's great for third harmonics. Third harmonics circulate inside the delta winding. And don't escape into the line. This keeps the system clean. And reduces interference. The vector group for this connection is DD0. Meaning zero phase shift between primary and secondary. You'll find delta-delta transformers in industrial applications where all three phases are balanced. Like motor loads. But there's a downside. There's no neutral point available. So you can't get a single phase supply from it. Next up. Star-star connection. Shown with the Y symbol. Here, all three phase windings are connected at a common point. The neutral. This is a very common connection. Especially for high voltage transmission. The big advantage here is that the neutral point is available. You can ground it. You can get single phase supplies from it. And it provides stable, balanced voltages. But there's a serious problem with star-star. Third harmonics. In a star connection, the third harmonics don't have a path to circulate. So they cause what we call neutral shift. This can cause severe voltage distortion. And overheating. To fix this, we often add a third winding. Called a tertiary winding. Or we use a solidly grounded neutral. Another issue is that unbalanced loads can cause the neutral point to shift, creating voltage imbalance. Because of these issues, star-star is not as common as you might think. Especially in distribution systems. Now let's look at delta-star. Probably the most common connection you'll see in practice. Here, the primary is delta. And the secondary is star. Why is this so popular? First, the star secondary gives you a neutral point. Which is essential for distribution systems. Second, the delta primary traps third harmonics. And keeps them out of the supply line. Third, this connection provides a phase shift of plus 30 degrees. Meaning the secondary voltage leads the primary by 30 degrees. This is really important when you're paralleling transformers. You need to make sure the phase shifts match. Delta-star is used everywhere. Step-up transformers at power plants. Step-down transformers in distribution substations. It's the workhorse of the power industry. The vector group for this is typically di11. Which means 30 degrees lead. One more thing. Because of the 30-degree shift, you can't just parallel any two transformers. They need to have the same vector group. Now the fourth type. Star-delta. This is basically the opposite of delta-star. The primary is star. And the secondary is delta. This connection is commonly used in step-down applications. Like in distribution substations. Here's what happens. The star primary gives you the ability to ground the neutral, which is good for system stability. The delta secondary traps third harmonics on the load side. And just like delta star, this connection has a 30-degree phase shift. But this time it's minus 30 degrees. The secondary voltage lags the primary by 30 degrees. The vector group for this is typically YD11. But depending on the winding arrangement, it could be YD11 or YD1. So if you have delta star with plus 30, and star delta with minus 30, the total phase shift between primary and secondary is 60 degrees. This is why you need to be careful when connecting transformers in parallel. Now let's talk about vector groups. Because this is where things get really interesting. The vector group tells you exactly how the transformer is connected. And what the phase shift is. Let's break down YD11. The first letter is the high voltage winding connection. Y means star. The second letter is the low voltage winding connection. D means delta. The number tells you the phase shift. And it's always in increments of 30 degrees. Here's how it works. Number 0 means 0 phase shift. Primary and secondary are in phase. Number 1 means 30 degrees lag. Minus 30 degrees. Number 6 means 180 degrees. Completely out of phase. And number 11 means 30 degrees lead. Plus 30 degrees. So YD11 means star on the high side. Delta on the low side. And the low voltage leads by 30 degrees. Why does this matter? Because if you want to parallel two transformers, their vector groups must match exactly. If you parallel YD11 with YD1, you'll get a 60-degree phase difference. Which means huge circulating currents. And damage. Vector groups are essential for proper system design. And protection coordination. Now before we wrap up, let me give you some practical guidance. When do you use each connection? Delta-delta is great for industrial loads, where you don't need a neutral. And you want good harmonic performance. Star-star is used in high-voltage transmission, where grounding is important. Delta-star is the most common for distribution, giving you a neutral on the secondary, and harmonic trapping on the primary. Star-delta is used for step-down applications, where you need a neutral on the primary side. Here are some selection tips. First, always consider your grounding requirements. Do you need a neutral? Second, consider harmonic loads. If you have lots of variable frequency drives, you need harmonic mitigation. Third, if you plan to parallel transformers, make sure their vector groups match. And fourth, consult the manufacturer's documentation for the specific vector group. One more thing. In many countries, the standard distribution transformer is DIN 11. Meaning delta primary, star secondary with plus 30 degrees.